Okay, so welcome back to the last talk of this morning, and we're very pleased to have Anna Loureiro from Kent, who's going to speak on special function positive solutions of the DP1 hierarchy.
Thank you, everyone. It's a pleasure to be here and to be in such an expert audience. I'm not an expert on this, but I've been very much enjoying working on it. Anyway, first of all, thank you for all the organizers and all the nice time we all had here, including yesterday. Maybe far too long time, but doesn't matter. Okay, so let's, what am I going to talk about here? Okay, as some of you may know, I work in orthogonal polynomials, and of course I wouldn't go away without talking about orthogonal polynomials. So consider, but the topic here is orthogonal polynomials with respect to Freud's weight, or generalized Freud weight, or whatever we may want to call it. But essentially, we are considering a weight with a potential that is a polynomial, and then some algebraic perturbation. So essentially, that's what I'm going to talk about all this time. And but the main focus will be on these coefficients beta n that you can see here, that are the recurrence coefficients of this orthogonal polynomial sequence. So this orthogonal polynomial sequence, because of the choice of the weight, it turns out to be a symmetric polynomial sequence, and that's why the recurrence relation only involves these three terms. But coming back to what I wanted to talk about is, okay, we are going to consider these weights, and we are looking at these recurrence coefficients. And now you may wonder, okay, but all of this is known. And most of it is true. So the idea is to discuss how we can add something that is perhaps new, or I hope so. Okay, so again, let's go into the details. As I said, the aim is to describe those recurrence coefficients. And it turns out that those recurrence coefficients are very much linked to the discrete Painlevé 1 hierarchy. And so let's take it slowly and go for the orthogonality definition, just in case, just to make it precise. So so I'm talking about orthogonality on the real line. So the support of the weight of the measure is on the real line, or on an interval of it. But this time, we are really going to consider the whole real line. Anyway, so given any weight, we can always, by definition, the polynomials Pn, so they always satisfy this three-term recurrence relation, although I don't like the name three-term because there's other polynomial sequences that are also satisfying a three-term but higher order. So it's a second-order recurrence relation. And as such, there exist coefficients alphas and betas, and of course it follows directly by definition on how we express them. Well, when the weight function or the measure is symmetric, then it turns out that these coefficients, they just go away. And that's the case what we are looking at, because we will focus on a case where our weight is a specific one, symmetric, and therefore we don't want the alphas. But anyway, there's always tricks, because we like symmetrizable things. There's always tricks to play around to go for the symmetric, from non-symmetric to symmetric, via quadratic decompositions or whatever. Anyway, but the betas are the ones we want to study. So of course we can compute them, we can do something, but as I said, the specification, is for a certain weight. And again, just going through a little bit on the background of orthogonal polynomial sequences, for a generic weight, I'm not specifying. Of course, these beta coefficients, they because of the algebraic relation you have, or the recursive relation, those betas can be expressed as determinants, and actually as a ratio of determinants and the so-called Hankel determinants. For a matter of fact, given any sequence of moments of a measure, one will say that the polynomial sequence exists and is orthogonal to that measure, provided that these Hankel determinants here are actually non-zero. But of course, computing determinants is not something so nice. But we take advantage of that expression. But as I said, we are dealing with a symmetric case, which means that the moments of odd order will all be zero. So we'll have a bunch of zeros here. And for computational matters, it turns out that we have great advantage of just removing that zero component from the determinant. And anyway, and in such a case, of course, the even order and the odd order will go in parallel. They are related to each other somehow, but we can compute them separately. And that's what we do. We just compute. So this is just a matter of addressing computation, nothing else. So, and of course, just follows by linearity that your betas and your gammas, and sorry, the betas can be computed in this way. So I see in the audience some bored faces. Of course, for those who work on orthogonal polynomials, they anyway, but be patient, bear with me, and we'll get there. Okay, so basically is what it can be used in terms of facilitating the computation or the numerics. And anyway, so coming back to the weight. But the weight, I said at the beginning, actually is a weight that can be written in this form. And it inherited, so it can be written in this something that is multiplied by this exponential with t to the x squared. And it comes directly from this type of weight. So remember, our weight is of that form, but the goal is with specific ones. So our weight is involving parameters like t and m, and it is of the form of exponential, sorry, x rho, and exponential of minus x to the 2m plus, sorry, bit of plus t x squared, okay? But it has that term. So it's even a simpler case of that. That's what, but no matter the weight, yeah.
Not a typo that is equal to t x squared.
Sorry? Yeah. It's the same. Because, no. Because this is, you're right, I should say m is bigger or equal than 2. Okay? Now it's exponentially small. Yeah? But yeah. So, of course, I'm not having here details, but the omega naught, of course, needs to obey to certain conditions. So in particular, we want a Schwarz function or with rapid decaying at infinities. And anyway, but the ANs and BNs that I was mentioning before on these expressions, these determinants, they can be also expressed as other type of determinants, in this time as Wronskians of whose components are derivatives of the first moment. But one may panic here, but it turns out that for most of these weights, we can relate the following moments to the boiled down to the first ones. And there's ideas that we can use from the study of other cases where actually things become very simple. Anyway, so because of the expression of the weight, because of that exponential there, is growing, but doesn't matter. T can be real. And then we have automatically the Volterra lattice equation for the recurrence coefficients. And no matter whatever omega naught we consider at the beginning, we always have this. And we can compute things. So this is known as the discrete KdV equation, or the Kac-Van Merburg, or the Langmuir lattice. Yeah, so it's known in several ways, but I'll refer to it as the Volterra lattice equation. So we're going to take advantage of this. We are going to use this to study, as I said, not to any omega, but even for this specific case with that algebraic perturbation. I'll explain why the algebraic perturbation in a moment. So anyway, again, we're still revising, still going through. And it is well known that those determinants, those Hankel determinants, the capital delta n's, they can also be written as an integral. And actually, it is the connection pretty much from there that follows the connection to random matrix theory, and because it is a partition function. Anyway, and it's also known as the Hein integral representation for the deltas. And, well, the polynomials, of course, by algebraically, we can also represent them as determinants. And it's kind of trivial. And often, it's even easier to not use the canonical basis here, but using a different basis to get advantage of the structure of the moments. However, we could use that technique to study such weights as we are doing there. However, it's not as evident that things would simplify greatly if we choose a different basis rather than this expansion into the monomials. Okay, so let's go a little bit of historical remarks for those of you who don't know. So there is a long relationship between semi-classical orthogonal polynomials and integrable equations. But perhaps the first one to come up with was Shoha. Then there was a lot of works during the 90s, or late 80s and early 90s, but and also in the 70s with Freud. But there were other semi-classical weights also considered. There were different approaches to the study, some more algebraic, some more analytical, but there was certainly ones that singled out to be studied later on, and that was the work, the proposal by Freud, and therefore the name Freud weights. And there was an enormous amount of contributions, but then somehow the theory went very steady. Nobody really paid attention till later when there was a connection to Painlevé equation, thanks to Focus, Alexander, and Kitaev. And also a great paper to read is Alphonse Magnus' paper, where it really gives, well, it's a funny paper, as Alphonse, for those of you who know him, is a very special person. And anyway, so this paper by Magnus actually gives a big insight, and there's other contributions to that study. But essentially, as I was saying, if we have a weight of this form, so if you relate to this case, would be with m equal to 2, And in that situation, what we have is that our recurrence coefficients do satisfy this do satisfy this this equation, the discrete Painlevé 1 hierarchy, but with only with n. And there is, of course, a connection to the Painlevé 4 equation, and there's lots of studies around, and the connection to these weights has been well known since a while now. So this equation that we are seeing is indeed discrete Painlevé 1, and there's a huge, long classification on that. I'll come to that. So Nalini and Cresswell did a lot of work on that, but I will get back there. Anyway, where was I? Okay, so let's go to this weight, finally. So we can see the previous examples with m equal to 2, m equal to 3. There's a lot of information there, but we don't need to restrict ourselves to 2, 3. We can continue. So it turns out if you continue, the first thing to do is to compute the moments. And the moments, they are by definition given by this expression. And if you compute the moments, well, it's kind of simple to get to these relations. I'm afraid that none of us know how to simplify this expression further. Perhaps Adri will find a way, but so far I don't know. But we are happy with this expression. We like hypergeometric functions. So any linear combination is fine with us. So most importantly is that, well, of course, the odds or the moments, they will vanish. They are all 0. And then regarding the even order moments, what happens is that, well, they will be the kth order derivatives of the original, the first moment. And as I said, if we go back to the beginning, we can look at as Wronskians of successive derivatives of the first moment. And again, that's all we need, actually. And we don't need to do differentiations, because nobody wants to do differentiations. All we need is to do shifts on the parameter. So this can hint why this is useful to have, but actually this algebraic perturbation also helps in other regards that I will talk in a moment. But in any case, the moments that have this linear combination of hypergeometric functions, I shall say here we have a 2fm function, but in reality it's a 1fm minus 1, because there's always, depending on the choice of the k, one of the parameters cancels out. Okay, but still having a 1f3 or 5, it doesn't, yeah. The generating function, yeah, I mean, the best one is pretty much similar to the integral. It's just the Laplace transform of that, yeah. Yeah. So that's, I think perhaps the integral is much easier. Or the differential equation is quite simple. Yeah, a differential equation in T. Don't know. Don't think so. No, definitely, no. But I didn't, yeah. Yeah. Sorry?
Like a factorial very much on top and a factorial in the denominator in your sum. Do you have to restrict the t a little bit?
No, they converge.
Okay.
Yeah, they converge. Remember K, sorry. Yeah. Yeah, I'm not in divergent, sorry. Okay. Yeah, but the moments, sorry, the moments do satisfy this differential equation. It's a rather simple one. It's just a representation. But it is what it is. but hypergeometric is fine. I like them, so it's okay. So in terms of going back, so the moments, as I said, are represented via that hypergeometric function or linear combination. We don't really care much about how complicated or simple it is. But anyway, but the polynomial sequence satisfying then the recurrence coefficients, as I said, mentioned, and I repeat it here, they can actually be written as the log derivatives of certain quantities that happens to be the Wronskians. And the moments, as I said, so if we go back before, actually I put here the expression for the moments, but actually what is more interesting is precisely this relation here, which then corresponds to a shift on the parameter. So the moments, then we can compute the betas or the recurrence coefficients in this fashion. And okay, so that's despite we have this expression for the moments, we are going to the idea is effectively these betas, they do satisfy a discrete Painlevé equation, and we are focusing on the case where we have these initial conditions. And it turns out that we do know that the solution is always positive, and that's the solution we're looking, because we are sitting these betas in the context of orthogonal polynomials with respect to a positive weight on the real line. So definitely those coefficients are always positive. They do exist, and then we just want to study further. So anyway, it turns out there's plenty of ways of deducing the equation for those recurrence coefficients. So one way has been done by some people, Banassi and Moro, and also Bonora Martellini earlier on. They developed in the integrable systems language a way of getting the expression for those coefficients. So basically, what we are seeing here is nothing but the Jacobi operator associated with the three-term recurrence relation of not the monic polynomials, but the orthonormal. So anyway, but it is well known that if you have a Jacobi matrix, is always symmetrizable. That means that you pass from to deal with the orthonormal polynomials. So then, of course, you can iterate. So essentially, what you can see is that these beta n's can be computed using basically the nth coefficient on the expansion of x to the 2m. Anyway, I won't enter to the technicality, pardon. So let's go back. And so basically, they can be seen. So what is this v to the 2m over there is nothing but you pick up this matrix. You can see that the 2m minus 1th power of it. And then you look at the n, at the row n, column n plus 1 entry. And what you get is essentially an expression that would give you for these vn's. Now, all the rest comes down as the compatibility conditions that arise on the fact that we are dealing with a weight of this format and the orthogonal polynomials associated to that. That's one way. There's many ways of expressing it. And then in particular, if you take m equal to 2, m equal to 3, and so on, what you find, so as you can see, what is arising there is nothing but the first bit of the dp1. And then here, it's not really, doesn't look like the dp1, but it's the dp12. I don't know how to call it, but I'll come to the notation in a moment. And all the rest, as I said, comes from the compatibility condition. But as I said at the beginning, I'm an orthogonal polynomial person. So I like to do it from the orthogonal polynomial way. So what I'm going to tell you soon is exactly what I've just said, but in a different language, if I may. So it turns out, okay, actually, no, I still have this slide to explain. Yes. So it turns out, well, as I said earlier on, Nalini, Joshi, and Creswell, they teach a lot of classification or explanation on this front, on the hierarchy of the DP1. And also the connections to the continuum limits of the differential equations. Okay, so effectively, you either using this method or the one that comes next, we deduce exactly the same equations. So this one is a special case of the DP1-2. Oh, actually, I wrote it here. Yeah, DP1 up 2 hierarchy, so the goal for us, let me take, oh, sorry, what am I doing? It's going back and forth. The goal for us is to study this kind of recurrence relations, okay, or to have a look again, or revisit these recurrence relations. Okay, as I said, I'm an orthogonal polynomial person, so I like to deduce from to explain from what happens in the recurrence on the orthogonal polynomial viewpoint. So it turns out that our weight function, being this one, satisfies this differential equation. And this is the Pearson equation, which appears, it's inherent condition to the semi-classical polynomials. And so either they are the discrete semi-classical or the Q semi-classical. It's always the Q Pearson equation, the discrete Pearson equation, whatever. But it's always a first order, ODE, with polynomial coefficients where the degrees of this one minus 1 and this one minus 2 is always bigger than 0. Anyway, so from this differential relation, it comes straightforwardly by integration by parts that you can express your, in this case, because of this x, you put the x there, and you do the differentiation, and you can actually, you look at the expansion of these polynomials, the derivatives, and in the sequence Pn. So basically, the coefficient to the highest power will give us the expression for the two highest powers will give us the expression for the equation that the recurrence coefficients satisfy. And it goes very simple. So you pick up this, you write like, we always can write it like this. The orthogonality means that you only involve 2 m terms up, 2 m terms down. Now you do integration by parts, and in a way, just using the orthogonality weight and playing around. And it turns out that those rows will actually satisfy these equations. But on the other hand, I can easily bring this equation into the 3-term, or this relation, or differentiate the 3-term recurrence relation, and then substitute, and compare, because it compare the coefficients in Pn plus 1, and so on, so forth. And then you will have alternative expressions for this, and that's where it comes out straightforwardly from the Volterra equation, what happens there. So you get actually the two equations repeated because there's a symmetry between those that are above the n plus k, or 2k, and the n minus 2k coefficient. So then we clean it up, and actually what we get in the end is precisely, the equations right here. So either way, take the method you like the most, but those are the equations we get, and we can continue on and on to m equal to 3, 4, whatever we like. So let's go to the weights. As I said before, lots has been done and lots of contributions, and I do not claim here to revisit all the massive contributions that came to the studies of the asymptotics of these recurrence coefficients in several aspects. So I'm not, I'm just quoting a few, nothing but that. So there's a lot of analysis on the asymptotic behavior of the recurrence coefficients of any, actually, you can consider minus x to the 2m and then any polynomial next to it. So here, well, we just take the tx squared, but actually you can have a tail of a certain polynomial, provided that that polynomial does satisfy a certain type of conditions. Or you can even add logarithmic terms. That's what is happening, again, provided that it satisfies certain conditions. And you can read, yeah?
So no condition in C?
Oh, T can be real. Doesn't affect.
No, but it's strange. Okay. I will ask later.
Yeah, I mean, you can even have Q, any a polynomial there of degree lower than 2m. Am I late? Oh, okay.
Yeah, okay. But it's not the varying weight.
No, not yet. No, I'm not doing. The varying weight is used to deduce this. Okay? Yeah, definitely. If there was the varying weight, I would not say. Yeah, it's okay. It's okay. So effectively, you can consider other polynomials or logarithmic terms, provided that we have functions that are of a certain variation or bounded variation condition that they need to obey to. Yeah? So in any case, the coefficients, they do behave as algebraic, as n goes to infinity for large n, they do behave as n to the 1m, and with some coefficient in front. Anyway, in terms of the zero distribution, this is also known, and here I'm adding the reference to Kellers and Van Asse, but actually their paper, and there's other papers on this, but they refer to this varying, so the zero distribution of the ratio asymptotics first to varying weights, which means that your recurrence coefficients actually grow with n. But there's other references. So in their paper is a bit more general than to this one. So actually this is not really what you will see in a paper, but we use the results there for their type of weights. Okay, it follows there's several contributions as well on this. Again, I don't claim here to quote every one, but what has been used was their results on the asymptotics. And it turns out that the zeros of, so here we are taking this, it's a rescaling, which is a typical thing to do when you're dealing with polynomials on unbounded support. Then we do this rescaling, and that's what, there's a second index over there that is being used. But the zero distribution follows this hypergeometric, or the Gauss function, if you like. And okay, so coming back to the quadratic Voigt weight, and so in this case, we're taking m equal to 2, just because it's simple. But then we will take it for m equal to 3, and I'll explain why we are doing this. So it is well known, and Nalini's talk at the beginning, Nalini gave a great introduction. And if you take the betas, you assume they behave all the same, call it beta, then you can look at the behavior of this function. Well, I put beta plus beta plus beta, which is 3 beta, yeah? But we all know how to solve this, and this gives immediately how the coefficients, so it kind of gives a formal asymptotic approach to how the coefficients behave for large n. And effectively, they will go around. But if we fill around the curve that comes from here, it's straightforward. It's an algebraic curve. We can solve it. And but it's but perhaps, sorry, Oh no, I'm sorry. It's coming. You need to be patient, isn't it? Okay, but when we look at this, there's clearly a flavor of even and odd terms. And if you do any computations, you feel that there will be a different behavior for the even ones, the odd ones. And that's, I shall say one thing here. This rho was the 2 lambda plus 1 before. But rho, I'll explain why rho is easier. So instead of looking at thinking of all the betas behaving the same, let's do this. So think about all the beta 2n's, the even order, to behave as a function of n. Let's call it u. Okay? And think of all the odd order to behave as a function of n. Let's call it v. So instead of looking at as before, all the v's, all the betas to behave like a function of n, now we consider the even order to behave as a function and another one. And then we have this coupled system of the two functions. But again, we are dealing with something that is quadratic, and we can solve it. Of course we can. And of course, they are related to each other in various ways, pardon me. And then we perhaps, and if we solve it, so here what are we looking at? So the u function, when rho is equal to 0, actually is even easier. So the v function is this one, is this blue arc, and then continues with this pale pink arc. So this curve that you're seeing here is exactly the beta curve that appeared before, the 4 beta times 3 beta minus t over 2n equal to n, okay? So that was the curve coming up here. And, oh, I forgot the term. I'm sorry. There's plus rho times, well, anyway. So when n is odd, then there will be a rho here. Anyway, but the curves, the u curve, when rho is equal to, oh yeah, I said rho equal to 0. Okay, sorry. Gosh, my mind. Anyway, so when the v curve, the capital V curve, will be this one that goes like this. Pardon, the capital V curve will be this one that goes like this, whereas the capital U curve will be this one. And there's a curve over there, of course. So if we compare with the little un's, so what we are doing here, oh, I should have added there. What are the dots that we are looking at? It's the beta, so the red dots will be the beta 2n's. And beta 2n minus 1. And wait. Yeah, that's right. Yeah. Oh, where's it? Okay. The beta 2n minus 1, so the odd order ones, are these dots that are being plotted. And it's effectively the curve. So if you look how they sit well, for large n, we did know that, right? It's no surprise. What it is surprise is that they are kind of sitting on the two curves. And there's a region here, there's a gap region where there's a bit of detaching from the curve. We can identify actually what is this interval that is a bit not so nice. Okay? Well, this is for rho equal to 0. But if rho is different than 0, then, well, we no longer will have this cusp over here, and everything smooths out. So one may say, well, with rho is a little bit more complicated, but actually there's a lot of advantage of using non-zero rho. And in terms of the behavior of those functions, there's lots of things that one can deduce directly from these equations, and they are kind of useful to understand on the actual little un's or the beta even order and beta odd order. It turns out, well, that the u functions are bounded above by the curve when you have non-zero rho. So when you have non-zero rho, the even order ones are bounded above by the curve when it is rho equal to 0. And the V's is the other way round. So they are bounded below by the curve when rho is equal to 0. So it turns out that when rho is equal to 0 is separating the two of them. And this gives us a bound. How about for negative rho? Now, negative rho, we need to be very careful. And I'll give a few more comments when rho is negative. But for the purpose of the curves U and V, capital U and capital V, for the purpose of the curves, there's this immediate relationship between them when we go for rho negative. But there's a caveat when we go to rho negative. I'll come to that because that weight will no longer converge. Okay, so that won't be the weight. But I'll come back to that, why we look at this. So essentially, we can see that all these curves, they sit like this. They are very, there's all sorts of monotonicity behavior and the minimums, and we can identify all this. This follows kind of straightforwardly from the coupled equation, but I'm talking about the curves where the dots will sit. Okay, so as I said, from the algebraic curves now with rho positive, oh, I forgot, there's plus. Can you see here? Plus rho. Okay, I did plus rho. Anyway, so when we compare, so we have these curves, and now the idea is to compare to the system. So now the little u's are the even order betas, the little v's are the odd order betas. So this is the discrete system, or the coupled discrete system. And here is the capital U as a function, continuous function of n. So what we are seeing here, well, is essentially the solutions of this system of algebraic equations, but it turns out we are looking for the solution where V is above U for other perspectives, which means this will be our V curve. We don't want this one, we don't want this one, and this will be our U curve. And now we should compare when we put the dots on top of it. And this is what happens. They really go very close. So in this case, we are taking rho equal to 2. And if we take rho equal to 5, it goes much closer. If we go back to the case where rho was 0, there was this gap. And I'm not claiming here there's no gap, because there is. As it is plotted in this instance, we can barely distinguish. But if we zoom in, then we will see there's a bit of separation between the dots and the curve, but not that big one. So for the sextic case, we have this dp1, 2. Am I okay with time? 5 minutes? 6? Okay. So anyway, so the m equal to 3 case, then you have this dp1, and then we do the same procedure, nothing new. But this time we are dealing with a cubic instead of a quadratic. It's okay, we still can handle this. And well, we just do some changes of variable, and now you can see that we can actually easily hold and study the curves in the new variables. I'm not going to enter into the detail, but in fact, what happens is very much similar. So this, what we are seeing is the sextic case, so m equal to 3 here, and with rho equal to 0. So there's this bit of detachment. When m is equal to 3 and rho is bigger than 0, this is what happens, okay? And you see, if we zoom here, there will be up, above, and below. There's no such thing as. In fact, this, oh yeah, I had written. So rho equal to 2. And if we do the difference between the dots and the curve, what you see is this gap. Of course, in this region here is the critical region, and we can identify it. It's precisely there's a gap that depends on t and on the choice of the t and the rho, of course. And there's an interval here where the dots are a bit distant. But I'm not sure if you can see, this is 10 to the minus 2. Okay? It's the biggest.
Do you do it in the other equation when rho equal to 0 as well?
Yeah.
So it's important that it is so large?
Oh, we tried. Okay, if you put t smaller, it's when it is large, the t large, it's when you can see a bigger gap. Where if t is, isn't it? If t is smaller, you don't see that big gap. So that's why I put the t20 to show a big gap. Yeah. So and as rho is bigger, actually it smooths a bit more. But that's not so surprising, because if we look at this, at what happens when rho goes to infinity, then it blends in with the n. Anyway, and here, if you see, it's 3 to the 10 to the minus 3. Okay, and here is 10 to the minus, I can't even see it. 10 to the 5 to the 10 to the minus 4. Okay? So that's what happens with n equal to 3. Then we can continue. So, and what about with rho is negative? So we need to be careful. Of course, we can only go up to minus half on that weight, because otherwise that is not the weight of any orthogonal polynomial system. However, the recurrence coefficients are defined per se. So there is an orthogonal polynomial sequence with those recurrence coefficients, even if you consider rho to be minus 5. But it means that this weight is not the orthogonality weight. Okay? But the recurrence coefficients, they do exist. There's no reason not to consider them. But we might not consider them because a simple reason. So look what happens. So this is with rho equal to minus a half, minus a quarter. So what happens is that the curve, so instead of following, remember that the little u's were following, so here when you change the rho, it flips. The u's become the v's becomes the u's in terms of relation to each other. And what happens is that now they are no longer following the blue curve that you're seeing here, but they are following this curve before. So the other solution, is also a solution to the coupled system of algebraic equations. So they are following this curve, and then they catch up to follow the other curve. So they jump from one side to the other. And the blue dots go like this. Okay? So the larger, the more negative the rho is, the more smooth this becomes. But the weight function is no longer that, I repeat. What about if you add this? But I think I'm exceeding time. I'm exceeding, yeah. So, yeah, you may wonder, well, are we adding just terms? Are we just playing around? Why are we putting this tau x to the 4? And actually, this brings a lot of fun to the picture. A bit more evolved, the analysis, and I'm very happy to have Marta here, because actually in work and a thesis was a source of ideas and things. Anyway, so the moments, okay, they are not good, but again, hypergeometric, who cares if it's a bit more hypergeometric, doesn't matter. The weights still satisfy a differential equation. slightly more complicated, but nothing special. It's all linear. It's hypergeometric functions, right? So then the recurrence coefficients, they do satisfy, well, there's a bit of more perturbation, but as you can see, there's a kind of a perturbation inherited from other things. And there's a differential equation for the recurrence coefficients. And now there was these early works where the people were looking at this potential and into different, so in some emission random matrices or models. Anyway, where people look at the beginning and at the late, and it was actually assumed or proposed it could be chaotic behavior in this critical region here. It is no chaotic at all because there's an order. Effectively, so I go to Marta, who is in the audience, and they looked at this kind of weights. There's no algebraic perturbation there, but effectively, the algebraic perturbation can actually help and smooth things out. Anyway, and it is they studied this, and what happened? They look at the curve that gathers all the data that comes from the recurrence coefficients. And as I said, there's no chaos over there because actually there's a lot of order. So these are the order 3n plus 1, and 3n plus 2 points. And there is clearly a curve connecting. Yes, I'm completely exceeding time. People want to have lunch. And so I skip, and I think. Thank you.
Any quick questions? Quite a few. Hang on. Let's go to Alexander first.
To the very last part on when you have capital N. When you have capital N, when you introduce this sort of here. So usually people consider this now as a varying weight, and you have both little n and capital N goes to infinity and keep some ratio. And there are very different regimes comparing to. But here you just still consider only n, little n goes to infinity.
So here, this is not our work. It's the work of Marta and Antonio Moro and doing. And they were considering this as a scaling and looking at the recurrence coefficients.
No, so the capital N fixed. And you consider large n. Yeah.
Yes. So it's not the two regimes. It's not the varying weights, yes. As we normally do for the asymptotic, yeah.
So what is the actual asymptotic behavior then of the beta-ns? Do you have formulas?
Sorry?
Do you have formulas for the asymptotic behavior?
Yeah.
Okay, but you didn't show them.
Sorry?
You didn't show them, right?
No, I didn't show explicit, but there's, well, in a way, I showed the leading term, but we have several terms down. Yeah.
Okay.
But there is one, yeah. Formal and not so formal, and there's more. Yeah, that is known.
Could you go back to 18 or thereabouts, where you had the one curve and the two curves? Yeah, that one will. Yeah, perfect. Further on. Next, sorry, I miscounted. One of the plots where it goes from the period 2 to the period 1.
Oh, sorry, after.
Up.
Yeah.
Yeah, that one.
Yeah.
So if you were, so that looks like from a dynamical systems perspective, you're looking at a period doubling bifurcation. And what would be really interesting, so you're starting from the left and going to the right, and that detaching is exactly what you expect to see. If you started from the right and went to the left, you'd see a really nice delayed bifurcation, a canard. So it would actually stick to the period 1 curve for an order kind of this logarithmic, looks like order 1 distance before rapidly jumping to the period 2, which would be kind of nice to see.
Yeah. And yeah, that definitely, and especially when it goes for the negative and to the transition, because they capture, they bounce. But I'm afraid my knowledge of dynamical system is not, maybe, I don't know.
Yes, why will we still have this picture? It is, I am kind of very intrigued, because when we, in our old paper with Blecher, considered, well, varying weight, when we had on the right-hand side little n divided by capital N, we have almost identical picture, but of course dependence on the limiting Rn on this ratio, on gamma. So everything that was to the left was 2 interval, and it was indeed jumping. And then we have 1 interval when it is greater than lambda critical. And in transition is given by Painlevé too. So, but it is, yes, it is a picture exactly the same.
I think it might
Yeah,
be
but
related.
it is
Yeah.
different functions. So here you have dependence on little n, we have dependence on gamma. There is a finite number of pictures. Yes.
But you see the picture for m equal to 3, if I plot it here, you don't notice the difference. Oh, yeah. Well, of course, there's difference in magnitude, but we don't really notice the difference, yes.
Okay, so thank you. Let's thank Anna again.
Oh, thank you. Thank you.
And back at 2 for the last talks of the day.
Oh, last.